Hi, good evening. My name is Nishu Virana. Welcome to my program. Today, I'm going to follow up from my last topic, which was thermodynamic system. And thermodynamic system, we covered mainly the control volume and properties associated with that. Now we are going to move forward towards the conservation of mass principle this time. So basically the conservation of mass principle is applied for a closed system. So it is an enclosed system and the mass cannot be created or destroyed. That's what the Einstein rule is. So the mass itself is a constant in the closed system. So as it says on the Einstein's rule, Albert Einstein's famous rule, mc squared equals mc squared, the energy can, the energy produced through moving a very small mass at the speed of light. Speed of light. So mass itself cannot be created or destroyed. So that applies. Therefore, the mass coming in to a closed system. Let's say closed system mass is constant, but this is for open system. Mass coming in and mass going out equals the total mass change of the system. So that is what a conservation of mass principle is. Now moving to the next part of the topic. Now in the thermodynamic system, we have what is called, if you go into the open system, which is you have a open section, so such as a piston. So in a piston you have the valves, so it is an open system. The mass coming in and mass going out, m in and m out, have to be monitored. So that's why it says mass coming in and mass going out have to be monitored in order to calculate the system mass. So one of the most important topics of in open system is the mass flow rate. The mass flow rate is the amount of mass per a unit time. The flow of mass to a unit area is called mass flow rate. So mass flow rate is actually proportional to the area, the normal area. So if you consider a duct, that's the area and that's the mass flow rate. So that mass flow rate is proportional to the area of the duct. So it becomes, is a derivative. So mass flow rate is, mass is usually rho times V. So rho times V and then dA. So that proportional side goes away, so that becomes that equation. So mass flow rate equals rho times V is the volume, and then A. But usually in a section that has constant change in the area, the mass flow rate, when the area changes, the mass flow rate changes. So we need to find out what the mean volume is. So if you look at go on a dot that's going in and that's going out, mass in. Usually the velocity profile is like that. So all these velocities, this is small velocity and this is high velocity. So we need to find what the average velocity is, so which is Vm, the mean velocity. So the mass flow rate equals rho times Vm times area. Area is the cross-sectional area. Now, moving into the further into the parameters of this formula. Now, mass flow rate, because in engineering calculations we calculate stuff in mass flow rate, and also we something called volume flow rate. So mass flow rate is actually equal to rho times the volume flow rate. M dot is the mass flow rate, V dot is the volume flow rate. So at the end of the day, volume flow rate equals A, the cross-sectional area, times Vm, the mean velocity of the dot or whatever the physical object that the flow is going through. That is the most important, one of the most important formulas in finding, calculating hydraulics, fluid calculations in engineering, hydraulic engineering. So I think that will pretty much cover the topic today. I think we will go into more detail next time in our thermodynamics system. So pretty much we covered the whole section of the thermodynamic system, and we will go into the pretty much the next part of the thermodynamic system. Thank you for listening. Bye for now.